interrogation spot right here. Okay, so let me introduce our speakers for today. Today the session is about Star Wars. No, I'm kidding. Well, maybe to a certain extent. I am curiously aroused by this slot because I worked a number of years at the European Space Agency, so I'm very emotional when it comes to the stars. And I also learned in that time that if you want to understand a thing or two about AI, you should really ask astrophysicists as opposed to AI engineers. Okay, so let me just say a few words about Forth, which is the Foundation for Research and Technology, Hellas, here in Greece. I actually saw there's a number of even research projects connected to Forth. It's very good stuff. About 1,500 people, am I correct? It's one of the largest impact-driven organizations in Greece. I'm a big fan of your work. So let me introduce Vasilis to give the presentation on AI and the frontiers of astrophysics and astrophysics. Please, floor is yours.
Thank you for the introduction and thank you for the invitation. So today I'm going to talk.
Move the mic closer to mouth.
Better?
Yes.
Okay.
Thank you.
So today I'm going to talk about bits, stars, and knowledge, and the boring title is AI at the frontiers of astrophysics. So before I start, let me tell you that the title was inspired by this book by Jared Diamond, Gans, James Campbell, but it has nothing to do with that book. So I was in a conference with a great presenter, and he gave a piece of advice that we should always start our presentation with a joke. Fortunately for you, I'm not going to do that. I have tried that several times. All of them failed miserably. So I'm going to start with the second best option that he provided, with a question. So the question that we're going to not exactly answer today, but just think about it, is what would it take for a foundation model to understand the universe, or the life cycle of our universe. So let's take this question in pieces. So first of all, let's start with foundation model. The foundation model is something, let's say, more general than an LLM. So it's what is behind ChatGPT, for example, is GPT. This is the foundation model behind ChatGPT, and it can be used also for other stuff like visual language models and other more models. So it's the core behind those fancy AI trend that we have seen recently. But it's more than that. So this, let's say, represents the bits part of the title. Now, this is we are asking about foundation model of our universe. So obviously the universe plays the role of the stars. But maybe more importantly, we don't want a foundation model or AI in general to just answer questions or predict the next token when we ask things about the stars or galaxies or our universe. So we want also AI or computers, a little bit more generally, to have an understanding of what they are talking about and not provide hallucinations or gibberish. So understanding is a very important part, and this represents the knowledge part of the title. Okay. So the question is, have we already reached this state? Are we already there? The answer is definitely no. We are far, far away from that. So in a surprising matchup that someone on LinkedIn posted, but I stick with that story, is that because there's also more testimonials that prove that something similar happens. So ChatGPT 4.0 played a chess match against an Atari from 1979 emulator, and surprisingly Atari won. even if Atari just had a very simple logic, looking ahead 1 or 2 moves, not the fancy LLM stuff that ChatGPT 4.0 has. So even with that simple logic, Atari won. And in fact, ChatGPT was not able to even make valid moves. So it mixed rooks with bishops. It forgot prior moves. It didn't go well, to put it politely. So we are still far from having a positive answer to the previous question. And by the way, since I mentioned that, I would also like to mention that, of course, most of you know that, but AI is not ChatGPT, so those are not synonyms. AI is not even machine learning, it's more than that. So AI was here many, many years ago, like 30 years ago, when the Deep Blue from IBM beat the world chess champion Garry Kasparov in 1996 or 97. And this computer over here, this software actually is not the screen, is also AI, but it's not a machine learning based AI. It just follows rules, complex rules, but still rules that beat the world champion for the first time 30 years ago. And of course, this part is called symbolic AI, if you've heard this term before. And there's also the part that is called neurosymbolic AI, which is a combination of symbolic AI, rules, logical rules, and LLMs or machine learning models. So you put some logical constraints to what the machine learning models predict or return as a result. And we are going to talk a little bit about that at the end of the talk. So what is this talk about? We will start with the bits part. We will see some of the recent advances in deep learning, not AI, but this specific part, AI. Then we are going to see some advances and challenges in astrophysics, the stars part. After that, we are going to discuss a little bit about the recent findings that we had in a symposium that we held 2 weeks ago in Athens, called University. And then we are going to cover the knowledge part and what we have been doing at Forth in the Parsec project. So let's start with our beloved bits. This is the Antikythera mechanism. This is the oldest known analog computer, and it was retrieved from a shipwreck in 1901 from the Greek island of Antikythera, and it took its name from that shipwreck, from that island. So 20 years ago, in 2005, there was a team from Cardiff University that used X-rays to read this over here, the fine print over here, that is actually a README, a user manual on how to use this computer. And based on that and the gears that they found using the X-rays, they found 37 bronze gears. This is a replica, of course. They understood or found some of the uses of this computer. So it was used to predict eclipses, even decades ago they happened. Fun fact, it was also used to predict, or not so fun, to predict when the next ancient Olympic Games would happen. And this machine was constructed some 1,000 years ago, so it was constructed 200 to 100 years BC. And machines with similar complexity did not appear again until the 14th century in Western Europe. So today, let's go to where we are today. Fast forward to 2005, a few months ago. This is the NVIDIA CEO Jensen Huang at Computex 2025, I think in Taiwan. And he's unveiling here an NVIDIA chip, the Grace Blackwell NVL72. And this chip includes a trillion parameter LLM. Okay, so we've gone from the 37 bronze gears a few thousand years ago to this chip from NVIDIA, which is probably the state of the art in AI processor architectures, as far as I know, at least. And it contains a pre-trained trillion parameter LLM. So we have advanced a little bit since the Antikythera mechanism. And how is it used? Why is it useful? It is useful because there are some recent advances in AI that require this computational processing and this the memory and GPUs and all this stuff. Some of the recent advances, again, by no means is this an exclusive list, just relevant parts for this talk. So we have foundational models for science. You might have heard about Cybert or Galactica or Flow. Those are all models tools that have scientific grounding, so they are not exactly the same as ChatGPT. Galactica, for example, is an LLM for science that has been trained on papers and available popular knowledge bases. We also have RAG, Retrieval Augmented Generation, for data, for querying data sets like catalogs for astrophysics, for astronomy. We have generative models like diffusion models and generative adversarial networks, or GANs. We have graph neural networks and graph transformers. And when we manage to model our data as a graph, which happens often, we can use those models, so we can train those models to provide vector representation of the data, what we call embeddings, and in this case graph embeddings. And when we have a vector representation of the nodes and edges in a graph, we can use those representations to find missing pieces in the data, missing links, for example. Or when you have two graphs like that, you can use graph neural networks and graph transformers to find the overlap between those two graphs. So align the two graphs or find the matches between the two graphs. We also have counterfactuals. You might have heard of counterfactual explanations, which help us understand how we got the answers that we got from an AI model, or rather how it would have worked if we made some slight adaptation in the input. A typical example is that when you make a loan application and it is rejected, and you want to know why it was rejected, the explanation is that if your salary was more than 60,000 per year, you would have the loan accepted. So counterfactuals is this kind of explanations that when you change the input, the output changes with a minimal way. So we have all those models in AI, all those advances in AI, and more specifically in deep learning. Now, from the stars part, here is the Starry Night. So in June 1889, Vincent van Gogh painted this the Starry Night, this painting. So this was just 1 month after he voluntarily admitted himself in a mental asylum, a few months after he got his own ear. And this is inspired by the view that he had from the window of this asylum. So at the time, Van Gogh painted the night sky just as humanity's understanding of the night sky was about to be shattered and rebuilt. Because at the time, in 1889, Albert Einstein was just 10 years old, and he had not yet expressed his theories that you might have heard of, and they played quite a big role in how we understand the universe today. So in that year when this was painted, the Starry Night, Milky Way was the universe for us. So for humanity, there was only one galaxy. This was our galaxy. The world was just the Milky Way. Now, that changed a few years later by Edwin Hubble in the 20s, but that's a different story. Now today, a bit more than 100 years from when the Starry Night was painted, when we thought that Milky Way was the universe, we have this effort, the Vera Rubin Observatory. You might have heard of it as LSST also. So with efforts like that, we are able to catalog millions, hundreds of millions, or even billions of galaxies today. This effort is about to be launched this year, although I have been using similar slides in courses that I teach, and it's always about to start that year, but it always gets postponed. But this year I believe that it will actually take place. It will actually start. And it will capture 20 terabytes per night. And in total, it will capture 60 petabytes of data. So it will take, let's say, a picture of the night sky every night. Now, if you think about 60 petabytes, if you take out your phone and you start taking pictures, and you take one picture every second, and you don't stop doing that until you reach 60 petabytes, you will reach 60 petabytes in 380 years. So that's a lot of data, if you think about it this way. And this amount of data will be available to scientists in every 6 months or so. I think that every few months or so they will provide the data publicly. And hopefully this will help us understand more about the universe and probably reveal answers to questions that we have not yet imagined. You may have seen, I guess, also this image, the first image of the black hole that was captured in 2016. Now it's a movie actually, because we have more pictures of that, so we can see how it progresses over the years. And we also have a second black hole in images. So we have two, and there are many more to explore. So, and here is Katie Booman, the person who led the algorithmic development behind this image. It took many scientists. It's not one person effort, of course, but she was leading the algorithm that is called CHIRP, I think. And this algorithm was basically a Bayesian model that took out the noise that was captured from the Event Horizon Telescope project. That was a project with radio telescopes positioned around the world, not just one telescope. So they combined the images from radio telescopes around the world, and the team's job was to remove the noise and make this image possible. So it was a big news in 2016, and it was presented in the CVPR conference, the algorithm. Now, some recent advances also in astronomy. It's not just astrophysics, it's more general than that, it's astronomy. Now we have the James Webb Space Telescope, and we have data from multiple wavelengths that we can use algorithms that have been there for a few years in computer science to combine, to fuse the data from those different wavelengths and have a unique picture, a single picture of what those sources, the light sources or point sources, tell us about those places in the sky, to put it more generally.
we also have this recent notion of astroinformatics, or at least I learned about it recently. I'm not sure if it's very recent, but I think it is. So astroinformatics is maybe Grigoris that will speak after me will tell you more details about that. It's about data science and astronomical data. So it's like statistics and on astronomical data. So we have cosmological simulations that, as I said, produce petabytes of data, and it's an opportunity for us, for computer scientists, to index, provide ways to index, query, and compute similarity of those data sources. And finally, again, this is by no means an exhaustive list. There is also this recent notion of citizen science. In computer science, we've heard that many years back. So what it is, you might have heard of the Galaxy Zoo. So it's something similar to Amazon's Mechanical Turk, actually, if you use that. Astrophysicists have a lot of data, as you saw before, and they cannot process all of them, so they ask humans, they ask other people that are not astrophysicists, mere mortals like us, to label data that they have trained them how to do that. So they give them some examples. This is an elliptical galaxy, this is a spiral galaxy, and then they provide more examples and ask many people to provide labels to the images that they see. Of course, not everyone does a good job, so there are inconsistencies, a lot of inconsistencies, and I think astrophysicists have used that recently, so we have used that for many years. So again, this is another opportunity for us to collaborate with astrophysicists and tell them how that worked for us, how weekly and semi-supervised learning worked for us, or active learning worked for us, and help them in this direction. So we have seen some advances in AI, some advances in astronomy, and a few weeks ago we had this symposium in Athens, at the Harkopiou University of Athens, that is called Universe AI, and this was an effort between me and a friend of mine, a long-time friend of mine, Yannis Leolakis, who is an astrophysicist. By the way, I forgot to introduce myself. I'm a computer scientist, I'm not an astrophysicist, and I'm an assistant professor at Harkopiou University and an affiliated researcher at Forth. So we had this symposium that tried to bring the two communities together, astrophysicists and computer scientists. And the idea behind that was that when I was talking to my friend Yannis, we discovered that there was some cultural crosstalk. So I was describing, describing my work to him, and I was talking about matching data from different sources, and he had a very confused face when I talked about sources. So we realized that for an astrophysicist, the source is not a data source, but it's a light source. So it's somewhere in the sky. This is a source for them. Then we also discovered that when he was telling me that he was reading a review, I thought he had written a paper and someone criticized the paper, but he was talking about a review paper, so what we call a survey, but for them a survey is something else. It's a collection of data over a large part of the sky. So we were using some common terms, but those terms meant something different for the two communities. There are some more examples there that I'm not going to describe. But what's more important is when we actually talk about the core of our work, like I was telling him about data matching and resolution, knowledge graphs, he didn't have much of a knowledge about these concepts. And when he was describing his work to me, like for blazars and quasars, I also didn't have much of an idea about that. He told me that there are big data sets that are available for anyone to use publicly. There are no privacy concerns in terms of lasers, so lasers don't care if we identify them. So it's a big opportunity for us that struggle to find good data sets and big data sets. So we realized that maybe it's a good idea to bring the two communities together, and that's what we a few weeks ago in Athens. So we had a few invited talks. We tried to have a mix of computer scientists and astrophysicists. So we had 12 talks, 6 of them more or less were for computer science and 6 from astrophysics. I'm saying more or less because there is a vague boundary for some of them that work in both areas. The last one, by the way, but not least, is the presenter that is going to present after me, Grigoris. So I'm not going to cover all the talks, but one or two highlights. So we had a presenter from NASA, Tyson Littenberg, from the NASA Marshall Space Flight Center in Alabama, and he described how AI has changed astrophysics, at least in his field. So he said that they have been using AI, not necessarily in NASA, I mean astrophysicists in general, in noise reduction, in computational efficiency, in event classification and source extraction, and he provided some references, some works that actually do that. I'm not going to present the references or the figures that he presented in my slide. And he concluded his talk with this slide. So he said that for gravitational wave detection, that's his field, interpretability is critical, and he emphasized on that. He put it twice in the slide, and in his talk he also emphasized on that. It's critical to have interpretability. So understanding how those AI models that do these tasks work, so that people can trust them. By chance, or actually not so much by chance, we also had another talk that was from a computer scientist, from a colleague of mine, Christos Diou, exactly on interpretability. So that's what we try to do, to present to each other that we have that. Is that useful for you? We need that. Do you have that? Okay, so this kind of interaction. And I think it worked. So Christos Diou presented his work on explainable AI. He presented a recent Python package that they released called Effector, and more stuff, but this was the part that I took from his presentation. So here, this is from a bike sharing data set, and they took some statistics, and they tried to explain on when was the peak in the bike sharing, bike renting. So for most works, explainability means understanding which feature is more important. So they try to, so this package automatically finds those features that are important and how they correlate to each other. So first, you see here two images. On the left, we have bike sharing data on a weekend or a holiday. So there is no big peak over here. The horizontal axis is the time. So around noon, there is a peak in the bike usage, bike rentals. On the right side, we see what happens during a workday. So the peaks that you see over here is when people go to work and when people get back from work. So one simple explanation on when we have peak spikes in bike rentals is during rush hours. This is not a big surprise, I guess. Then, if you use this tool to explain further the features that are important, they found out that what other feature? The temperature is important as well. Okay, this is, I just took the temperature in addition to the previous feature, which is the workday, and they found out that when temperature is low, there is a smaller peak in work days compared to when the temperature is high. So if you keep everything else the same and you change one feature, this might have a big impact on the result. So I'm not going to go in the details of how these methods work. I'm just going to present the highlights. If you're interested, please find me after this talk to provide more details. Then we had Themis Palpanas from Paris Descartes, or I think this is changed, or the French University Institute. He talked about anomaly detection and similarity search. This is one of the things that I told you that's a big opportunity for us to compute in the previous slide about the latest advances in astrophysics. So he presented two parts, similarity search and anomaly detection. In the second part, he presented a work that was published in VLDB 5 years ago. And in this work, he mentioned that they have a nice way that when they get time series as input and some input parameter that is the length, they can transform this time series into a graph. And then when they have this transformation into this graph, it's very easy for them to detect anomalies. And this method is called series to graph. So for astrophysicists, anomaly detection is a very interesting topic. But probably the most interesting talk, at least for me, apart from Grigor's talk, of course, was the one given by Torsten Lensley. And this is a person that is behind the German Center for Astrophysics. And this is a research center to be founded in Görlitz in Germany, in the German-Polish borders, probably later this year or early next year. And this has the ambition to become the largest astrophysics research center in Europe. What was very impressive for me as a Greek is that they have a 15-year plan. This is unimaginable for Greece. We have a plan that goes so far. They plan to have 1,000 employees in 15 years. And Torsten is leading the data science sector of this research center. And he was actually carrying in his pocket this thing over here that you cannot see very well. This is a 3D prototype of what he calls the Milky Way Atlas. So they are trying using data fusion, probabilistic data fusion, to get information to build a map of our Milky Way galaxy. And he had the 3D model in his pocket that he passed around to the people, and he made sure that he collected at the end of his talk. So that was really impressive for me. And of course, I'm not covering everything. There were many more interesting talks about VLMs in radio astronomy, diffusion models. Federica Bianco was representing the Vera Rubin Observatory, so she described when this is about to start, and she was quite sure that it will start this year, so I take your word for that. And we also had some other talks, like one or two foundation models for astrophysics. So we are getting we're getting closer to a positive question, a positive answer to the question that I posed at the beginning. Now we covered bits and stars, superficially of course, and what about the knowledge part? So for me, this is the key factor in how we proceed in AI and astrophysics. So this is Aristotle, and he was among the first to start the reasoning. So what is called syllogism. A popular example is that all men are mortal. Socrates is a man. So if those two sentences are true, then we can deduct that Socrates is also immortal. Socrates was the teacher, Plato was the teacher of Aristotle. So from that, we have gone to today, or actually a few years back, to knowledge graphs that are built. The theory behind them is, the theory behind most of them, not all of them, is coming from ontologies. Ontologies come from description logic, and description logic comes from first-order logic. It's a decidable fragment of first-order logic. So we use ontologies and knowledge graphs every day, even if we don't know them. So if you do a Google search and you see some structured results on the right-hand side, for example, if you look for Leonardo da Vinci or Vincent van Gogh, you will see some structured part on the right side with some pairs of attributes and values, when the person was born, when the person was died, what they are known for, where they lived, things like that. All those information have been gathered by Google, by the project that was at the point called Knowledge Vault, from Luna Dong and her colleagues 10 or 15 years ago, maybe more, if I'm not mistaken. So they had, of course, the big indexes of Google about the web, all the HTML pages. They did some mining, regular expressions, and much more fancy stuff. And they had the probabilistic data fusion to model, to capture what they know about every entity that is there on the web, like Vincent van Gogh or Heraklion, or this symposium that we are here right now. So, before I describe more about knowledge graphs, let me give a very high-level overview of what they are. I guess most of you know about them already. So they are built around classes and properties and individuals. A class is a group of entities that have something in common, like celestial bodies. A subclass is a specific subtype of interest, like galaxies are a subtype of celestial bodies, and Milky Way is one instance of a galaxy, or one individual, as we call it. And there are also some properties that connect the individuals, like the property connects Milky Way and with Earth. So Milky Way contains Earth. So we have those classes, subclasses, properties, and some other fancy stuff that we call actions. Well, I think we shouldn't call them actions, but anyway, that we can use to help machines understand the data and perform reasoning. So that's the strong point of ontologies and knowledge graphs. So exploiting knowledge graphs for deep learning tasks has shown impressive results in the last few years. For example, ontology matching works that rely on GNNs, graph neural networks, have shown that they beat state-of-the-art approaches before that. Convolutional neural networks, CNNs, have been used for image classification. So the example that I described before, when you see an image of a galaxy, you can use a CNN to classify it, see, for example, if it's a spiral galaxy or a galaxy of a different type. We have been using GNNs to answer questions and build chatbots, even before ChatGPT, or provide single one-shot questions to answer. And we have been using GNNs built from knowledge graphs to understand what is the content of a text snippet. So when you have a text and you have a knowledge graph, we can understand, we can split the sentence in different parts, in different tokens, and understand which part is referring to something that you already know and you have stored in your knowledge graph. So we have been using that for years. On the other hand, other than image and signal processing, that is mostly what I described to you so far about AI and astrophysics, the way that astrophysicists conduct a large part of their research is far behind the latest advances in computer science. for example, when it comes to text processing or tabular data processing. A common scenario is that they start from reading papers, publications from archive journals and online catalogs. They actually read them. They don't have an AI process them. Then someone reads the tables, tabular data from those publications, and tries to combine the tables that they find from different publications in one place. They also cross-check with online catalogs like Simbad, Aladdin, Vizier, Hyperlida, and NED, and other catalogs that are available online. And this process is so labor-intensive that when they do that, many times it's enough to get a PhD just by doing that. It takes a lot of time and it takes a lot of expertise. And when they do that, it also gets a lot of citations. So there's this, just an example. This is a paper called from Carl Heile, 9,1286 star and agglomeration polarization catalogs. It was published in 1999. It has received more than 600 citations, and it does exactly what I described, this process that I described. Now, you may think that 1999 is a bit old, and today things have changed in how astrophysicists do their research, but that's not really true. This is the Heraklion extragalactic catalog that was the work of astrophysicists at Forth, the Institute of Astrophysics in Forth, and it was published 4 years ago. The first version was published 4 years ago. And again, it follows the same, it involves the same painstaking process that I described of going many catalogs, having many students read those catalogs and publications and try to combine them in one place. By the way, since today you're visiting the Skinakas Observatory, this is a picture from the Skinakas Observatory of the M51 galaxy. So this is a catalog of galaxies, and it contains around 200,000 galaxies within, I don't remember the exact number, I think 20 megaparsecs. So we have good news, some good news. Today we have catalogs, online catalogs like Simbad. I'm not sure if you can read most of this stuff. So this is a page from Simbad that is describing the star Sirius, the brightest star in the sky, the night sky, and it contains some information like this is the alpha star of Canis Majoris, and it has a picture of this, an image of this star, and here it has also some identifiers. I cannot read that even from here, so I'm describing what is happening over here. So here we have some analysis of how you can find this star in different catalogs, like synonyms or different identifiers. Now this looks great. It seems that it's solving the problem that I described before, but the problem is that this information is mostly provided by people that publish their own data. So it's a push-driven. It's generated by the people that generate the data, and they inform Simbad that I have this information, so please include it in your data. So it's not yet, there's not much automation yet. Now the bad news is that, okay, someone might ask why don't we use our very well structured and wiki-based knowledge graphs like Wikidata or Wikipedia. Let's see an example from Wikidata here. Okay, this is a description of active galactic nucleus, or an AGN. We have a nice textual description here that says that AGN is a compact region at the center of a galaxy that has a much higher than normal luminosity, etc. So this is a correct description, but when we look into the structured part, here it says that an AGN is a subclass of a galaxy, so it's like a special type of a galaxy. But the truth is, also based on this description, that it is a region within a galaxy. It's not a galaxy itself. So we didn't get that right. And also that a synonym of active galactic nucleus is an active galaxy, which is again false, because an active galaxy is a galaxy that has an AGN. So, okay, let's look at Wikipedia then. Another popular knowledge base or knowledge graph, depending on how you see it. Again, we have a textual description, pretty much the same as before in Wikidata. But here we have another problem. We see that an AGN here is an entity of type settlement, which looks really wrong, and it is wrong. So if we wanted to consult those two knowledge graphs to combine the knowledge that we have, we would end up with inconsistencies. We would be confused about what knowledge graph that knowledge graph concept actually means. And it was very easy to find an example with such inconsistencies. I tried like 2 or 3 queries, and this is something that came up. So now we have this project at fourth. This is a fourth synergy project between the Institute of Computer Science and the Institute of Astrophysics, and it's called Parsec. The idea behind Parsec is that we want to automate exactly this process that I described before. So instead of having humans read the papers and the catalogs, we start again here from publications from journals, online journals, and online catalogs like Simbad that I showed you before. We extract the data and metadata, like who are the authors, when was the paper published, where it is available, and using something that I will describe later, semantic annotation or semantic table interpretation, a neurosymbolic approach, using both LLMs and rules. We are not there yet, it's still the first year of the project. We aim to get here to a knowledge graph that combines the information that we get from all those publications. So we call that a semantic catalog. It's really a knowledge graph, but sometimes people are scared of having this term, so we call it a semantic catalog to sound better. Once we have this semantic catalog, we can build a next version of Hecate, the Heraklion Extragalactic Catalog. This is actually version 3 that is going to be published at the end of the project. This is a catalog about galaxies, and we also apply the same knowledge graph for a different use case to describe supernova remnants, SNRs. So based on the same knowledge graph, we try to build 2 catalogs for 2 different use cases. As I said, we try to automate this process as much as possible, but it's not, I don't think we're going to fully automate that. So we have this place here in the middle. This is more or less human in the middle, human in the loop. So for things that we're quite certain that are correct, we go directly from the tabular mining to the knowledge graph, and we add the information there. But there are some other things that we may not be sure if they are correct, or if we added them here, it will make a big change. And for those type of changes, we make a change request to a catalog curation committee, CCC, that will discuss this change and apply the change or reject the change if they disagree with that. That's the high-level picture of the project. We have a first version of this knowledge graph, and we are working in the data mining and table annotation process. So for the first version, we have publicly released 2 resources. The first one is an ontology. It's still in its infancy, I would say, so it has still 15 classes and 80 object properties and 15 data properties, so around 30 properties in total. And it describes, it's not something specific to Hecate, so it describes measurements that exist in tabular data from publications. Should I wrap up?
A few minutes.
Okay.
3 minutes.
Okay. We have also released a knowledge graph that we call Hecate knowledge graph that follows this ontology using 2 different approaches, but this is not important how it was created, the technology behind that. It has resulted in 44 million RDF triples that take around 5 gigabytes of space uncompressed. And again, we have publicly released those resources on Zenodo. Now this is an example of how this knowledge graph looks like. If you start from the table at the top here, it describes a galaxy that is identified by NGC 97, and this is the tabular version. This is a small part of the knowledge graph version of this galaxy. So we have information about its distance, 67.9. So we have here its distance and some error margins of how certain we are about this distance. So it's plus or minus 12.5 megaparsecs from this value. This is a small part of this knowledge graph. The ontology is more complicated than that, and I'm not going to describe more details on that. But if you're interested, again, I'm happy to discuss this after this talk. And this is again publicly available, and we are already working on enriching it with more classes and more properties to make it publicly available and cover more use cases. Now the last part is the tabular data mining. This is the part I'm mostly interested in. The idea here is that we read PDFs or MRT, machine readable transcripts from, I think these transcripts, but anyway, machine readable files from astrophysics papers. And we try to perform some tasks. If you are familiar with the International Semantic Web Conference, we have a challenge there, Semantic Web Challenge, the SEMTAB challenge, that the tasks are related to when you have a table and a knowledge graph as a target. You try to understand what the table is about using the knowledge graph concepts. You try to understand what each cell is about, or what each column is about, or what is the relationship between the columns. And for that we use a neurosymbolic approach. So we ask LLMs for simple queries like what is Switzerland, what is US, what is Canada. This is not an example from physics, of course. And then we try to infer logical rules and apply logical rules to reduce hallucinations from LLS and reduce the search space for correct matches. So this is something that is still work in progress. We have not yet published something in this task. So, conclusion. Okay, to summarize the conclusion slide, we can no longer have. Actually, we can have astrophysics without AI, but it will fall behind the state of the art. And it seems also from the symposium that we organized 2 weeks ago that you cannot go far beyond state of the art today in astrophysics without using at least some of the AI tools that we provide. And for us computer scientists, it's really important to use big data sets, and a big opportunity for us is to use astrophysics data with their challenges. Of course, they are mostly numeric data. They are not as easy as the table that I showed you in the previous slide. And ontologies or knowledge graphs in general offer a bridge between the deep understanding and raw data, and they are grounded in tools that have been produced for years, and they are grounded in first order logic. What we plan for the future after we end up when this project, we plan to go beyond that if this project succeeds, of course, and try to have a federated, semantically annotated knowledge graph, not just about astrophysics, but in general about scientific knowledge. So digging not only into astrophysics publications, but also in other fields. And of course, we want to have that in an explainable way, and so that it's trustworthy and it's accessible by more than astrophysics or computer science experts. So I think that's all. Thank you.
All right, let's thank our speaker. Thanks a lot. Very, very cool. We have time for, I would say, a couple of questions. I'm standing between ourselves and our coffee, which is sitting around the room outside. Any questions, thoughts, remarks, issues, doubts, curiosities? Anyone? I have one. I'll keep it to one, and a comment. But I want to give you the space first. Yes? Please.
Thanks, Holger. You mentioned sometimes that you are using large language models for understanding this data. As far as I understand large language models, they are typically based on the idea of tokens, single characters or a sequence of characters or some other kind of defining tokens. How do you define tokens in your domain in astrophysics?
That's a very good question. So, first of all, I'm not an astrophysicist, so it's not my domain. I'm a computer scientist, but I understand what you're talking about. So for us, we are dealing mostly with tabular data. So we are targeting this mining part over here is that we just extract the tables from publications, and so far, and what we plan to do is to also extract the text part of publications that is relevant to tables, so like the table caption or the surrounding paragraphs. So in that sense, tokens can be thought of like cell contents. Okay, so they are the contents of a cell, which is typically or the column headers, which are typically one or two words or a number. Okay, so so we use LLMs for that, but the more interesting part. So for LLMs, we're not building something new. We're not building a new LLM. What we are working on mostly is about how we correctly ask the questions to LLM so that it doesn't provide hallucinations. So we try to automate this rule mining part. So when you see, for example, a column that is about distance, we want to restrict the possible answers to something that has to do with a positive number or some number that we don't expect to be larger than something that we know, it is a known distance in the galaxy, something too far away or something with a negative distance. So we try to restrict the possible answers that we get, and we try to detect and exclude incorrect numbers, or sometimes astrophysicists, I don't know if it's a common term, they call it the magic numbers. So when they don't know what to put in a cell, they put some random number or very high numbers that when you read it for an astrophysicist, it's obviously something that you know is wrong. So they put these kind of values instead of nulls, and they put these values to say that I didn't have the right measurements for these values, or there is no point in having a number in this cell. So for the LLMs part, I would say we are just using some open LLMs that are available, publicly available and free, but we are mostly investing on the rules part. I know I didn't give you a good answer, but
I get an expression. Thank you.
All right, thanks. Any further questions, thoughts, doubts? Okay, I have a question, but I'll take it offline. I don't want to hold you hostage between ourselves and the coffee. So the coffee break should be outside and already ready. Enjoy it. Come back sharp in like 10 minutes, 15 minutes. Is it more? How many?
50 minutes.
Okay. See you back here. It's very interesting. All of them. What is a European program? Ah, yes. Yes.
I found my job.
Yeah, I actually want to use it. Test it in all sorts of students. In fact, start from. No, I mean also the survey. One of our kids on the last part, that's what I was asking. There is an internal form.
It's an internal form.
By the way, Indigo here is our kids lots of I should definitely have a child.
We have also someone using which is somehow
Yeah, they are in there. So
using